Stanford University.
Okay, if we're ready, let's go then. We talked last time about angular momentum operators, and I started to show you how the algebra of the angular momentum operators works, how multiplets with different angular momentum have certain numbers of states, and the states form, they're called multiplets. I'll come back to them in a minute, but let's just talk more generally about what angular momentum is about. A good example is an object, a particle, moving in a central force field. Here's the center. Particle moves around in a central force field. It has a radial position and an angular position. The angular position really means two angles, an azimuthal and a polar angle. So it's a three-dimensional system. And the angular momentum is conserved. The angular momentum is a vector, and the angular momentum always is in the plane perpendicular to the motion, plane perpendicular to the orbit. So there's the angular momentum. The orbital plane is perpendicular to it. And because the angular momentum is conserved as a vector, the orbital plane is also conserved. The orbital plane stays the same, but of course the radial position moves around in a circle. Not a circle, take it back. Moves around in some orbit. That's classical. That's classical. Quantum mechanically, the particle is described by a wave function. The angular momentum operator has to do with the angular dependence of the wave function. In general, the wave function in a situation like this would be a function of position, of course. It's always a function of position. It could be a function of x, y, and z, but you could also write it as a function of the radial coordinate, the radial distance, and two angles, polar and azimuthal angle. We talked a little bit the first time, maybe the last time, I can't remember. We talked a little bit about angular momentum in two dimensions. Let's go back to that for a moment. If everything was in two dimensions, then the angular momentum would just be the generator of rotations about the perpendicular axis here, and its structure as a quantum mechanical operator would just be angular momentum is equal to minus I times the derivative with respect to the angle. That's the analog of momentum being minus I times derivative with respect to position. What it tells you is how the wave function changes with angle. So let me just remind you, if you look for angular momentum eigenstates, then what you're looking for is functions which satisfy minus I d by d theta. Let's say functions of r and theta. In two dimensions, we don't have to worry about phi, just r and theta. And if we're looking for an eigenvector of the angular momentum, we want to set that equal to a number, the eigenvalue, L times psi of r and theta. It's a little differential equation, and it doesn't really depend on r. R is just a spectator here. The derivative is with respect to theta. So this is an equation about the theta dependence, and it doesn't really care about r. We know what the solution of equations like this is. The solution is psi equals e to the I L theta. E to the I L theta, where L has to be an integer in order that the wave function comes back to itself when you go around the closed curve. Well, what about the r dependence? What should the r dependence be? This doesn't tell you what the r dependence is. So the answer is you have an angular momentum eigenfunction no matter what. Let's not use the same function. Let's use a different function. Let's call it chi of r. Any wave function that looks like e to the IL theta, it doesn't matter what its R dependence is, it will be an angular momentum eigenstate. So angular momentum has to do with the angular dependence of the wave function. The radial dependence is irrelevant to the angular momentum. It may be relevant to the energy, but it's not relevant to the angular momentum. And the same is true in 3 dimensions. In 3 dimensions, angular momentum also has to do with the angular dependence. And there are particular wave functions, generally arbitrary functions of radius, doesn't matter what they are, times specific functions, they're usually called y, of theta and phi, which are analogous to the e to the IL thetas. And those wave functions are the things which determine the angular momentum of the state. They're the things which change when you rotate the configuration, and angular momentum has to do with rotating configurations. So when we talked about angular momentum eigenstates, we were really talking about these functions of theta and phi. Now, it's awkward to worry about theta and phi. We don't have to. What we did last time was we used a bunch of tricks. So let me go back to those tricks and remind you, but keep in mind, at every stage, what we're talking about is the angular dependence of wave functions. Okay, let's recall what we learned last time. We started with the angular momentum operators, Lz, Lx, Ly. We found out that they have certain commutation relations. Lx with Ly equals ILz. There's h bars in here, but I'm not going to belabor them. I don't care about them right now. Lx, Ly equals ILz, and cyclic permutations to more like it. All right. Then we started to play some games. We played some games because Dirac taught us to play those games, not because any of us would have been smart enough to figure them out ourselves. I don't know, maybe we would have, who knows. But the trick was to construct, well, to pick one of the operators and work in the basis of that operator. In other words, pick Lz and work with eigenvectors of Lz with eigenvalue m. We don't know offhand what the spectrum of eigenvalues is, but let's just postulate, or let's just define the eigenvalues to be little m. Forget for the moment whether they're integers or not. They may or may not be integers. But this defines the eigenvector of Lz with eigenvalue m. And we worked in that basis, and we found, to our great joy, that the operators Lx plus or minus I Ly, which we called L plus or minus, had some nice properties, were useful. I'm not going to write down the properties. You have them written down from last time, I hope. They follow. The properties follow. It's commutation properties. They follow from the commutation properties of the L's. But here's what we learned. We found out that if we start with an eigenvector of Lz with eigenvalue m, and we hit it with L plus, I guess, forgot whether we put the pluses and minuses upstairs or downstairs. Doesn't matter. What did that do? That gave us another eigenvector with m plus 1. We worked out that was a consequence of the simple algebra of these commutation relations. We worked it out by just sticking in the equations. It was a couple of lines. And we found out that L plus is a raising operator. This is called a raising operator. If this line represents the spectrum of possible values of m, is 0, and so forth, this tells us that we found another eigenvector which is 1 unit up. It has not yet told us anything about whether the m's are integers or not, but it tells us that if we find one, we can find another one by hitting it with L+. Likewise, we can find another one by hitting it with L-. So L+'s and L-'s are operators which take you up and down the spectrum of eigenvalues of Lz. Okay, that was the first thing that we discovered from the algebra of these things. The next thing we asked was, well, does this go on forever and ever and ever? It will go on forever and ever and ever unless it comes to an end. How can it come to an end? The only way it can come to an end is if L+, instead of giving another non-zero eigenvector, gives us 0. That's the only way it can come to an end. And if it does come to an end, and typically they do come to an end, if it does come to an end, that's the end of the spectrum of raising that you get by raising. And let's suppose that's over here. Then we have things separated by an integer, but we have one more thing that we know. We know that the z-axis, that there's nothing preferential about the plus z-axis. If we simply rotated the whole picture around and replaced the plus z-axis by the minus z-axis, all the rules would be the same. So for that reason, the spectrum has to be symmetric about the origin. Anything you can say about Lz, you can say exactly the same thing about minus Lz because they're just related by rotation. So if the spectrum ends at some point here, it has to end going downward at exactly the same point except reflected. Now, each action of L+ or minus displaces you by an integer. How is it possible to come to an end with the ends being symmetric like this if they have to be integers? For example, if this point was at 3/4 here and you kept going down, 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 you would never come to minus 3/4. Is that right? Yeah. You'd never come to, yes, you'd never come to minus 3/4. The only way that it can happen, that you can end and be symmetric, is if you start at an integer. That's one possibility. Let's say this is integer 2 here, and then end at minus 2. That's one possibility. And the only other possibility is that you start at a half integer. For example, the simplest case would be that the spectrum ends at a half and ends in the other direction at minus a half. That's still separated by an integer. In that case, L+ would take you from the lower state to the upper state. L- would take you from the upper state to the lower state. But what would happen if L+ hit the upper state? It would give 0. If L- hits the lower state, it would give 0. So that's the way we know what the spectrum of the angular momenta is. The spectrum is either integers or half integers. And each collection of states like this, if it ends at some highest point, which is usually called, let's forget the half integer case. The half integer case will come back to us, but probably not tonight. Let's take the integer case. All right. Could end over here. Is 0, 1, 2, 3, 1, 2, 3, end over here. So there'd be how many states? 1, 2, 3, 4, 5, 6, 7 states here. 7 possible states. The highest state has the maximum value of m before it's killed by the next action of the operator. the maximum value of m is called L. L equals the maximum value of m for that particular collection of states. Minus L is, of course, the minimum value of m. And so the values of m go from minus L to plus L. And then nothing beyond that from above, nothing beyond it from below. How many states is that altogether? If you go from minus L to plus L, 2L plus 1. Okay? So a multiplet, a collection of states is characterized with a given value of, well, we'll see what they have a given value of, but a collection of states of this type, a multiplet, has typically 2L plus 1 states. 2L plus 1 states. That's the first thing we find.
Or an infinite number of states.
Could have it, that's the other. Sure, that's just L equals infinity.
Right.
Right.
But that is a possibility.
It is a possibility, but it's not one that we're going to worry about. They're pathological. The reason they're pathological, for a variety of reasons, a lot of the reasons that they're pathological, but among other things, energy usually depends on the angular momentum. As you increase the angular momentum, keeping other things fixed, the energy goes up. And if you're interested in states of finite energy, then you're not interested in states with infinite angular momentum. Okay, let's do one more little exercise. What characterizes these multiplets? Well, I'll tell you what characterizes these multiplets. It's the magnitude of the angular momentum. All of the states in this 2L plus 1 collection have the same value of the magnitude of the angular momentum. Now, what do we mean by the magnitude of the angular momentum? What we mean by the magnitude of the angular momentum is exactly what you would mean in classical physics, or I should say the square of the magnitude of the angular momentum. It's the magnitude of the angular momentum vector squared. And that's equal to Lx squared plus Ly squared plus Lz squared. The only difference between classical physics and quantum physics is these are now operators. They're not just numbers in the usual sense. They're quantum mechanical operators. And let's see what we can find out about L squared. In particular, L squared for a multiplet of 2L plus 1 states. In other words, supposing we have a multiplet which terminates from above at L, terminates from below at minus L, what can we say about its L squared? Okay, so here's the tricks. And they're all tricks, but they're nice tricks. This is equal to Lz squared. Now, first classical. Lx squared plus Ly squared, that's plus Lx plus I-Ly. Do I want that? No, I want Lx minus I-Ly. Times Lx plus I-Ly. This is Lx squared plus Ly squared, and the cross term is 0 classically. So this is a correct equation classically. It's not quite right quantum mechanically, and the reason is that Lx and Ly don't commute. We actually have an extra term here. We have the extra term, let's see what it is. It's I, Lx, Ly, that's this product, and then minus I, Ly, Lx. So it has the commutator of Lx, Ly in it. Sorry, the commutator of Lx and Ly. Yeah. In other words, we've overshot by writing in Lx minus I-Ly times Lx plus I-Ly. We have to subtract this, minus I, commutator Lx, Ly. That's just the extra piece that's there because Lx times Ly is not equal to Ly times Lx. Okay, so that's straightforward. But what is the commutator of Lx with Ly? Lx with Ly is ILZ. So this is equal to Lz squared. Now, we're going to get an I from the Lz. There's an I here, and then there's another I from the commutator. I times minus I is plus 1. So this will give me plus Lz, Lz squared plus Lz, and then we have plus L minus times L plus. Okay, you with me? That's L squared, the square of the angular momentum. Now let's apply that. Let's take this operator and apply it to the maximum highest M state. M equals L. M equals L. So let's take this L squared on L. L is the highest state there, okay? What do we get? We get Lz squared on L plus Lz times L plus L minus L plus times L. Okay, first of all, what is this script L here? It's an eigenvector. Remember what it stands for. It stands for the eigenvector of Lz with the highest possible value in this multiplet. What is Lz? Lz is equal to little l. In the state up here, Lz is equal to little l. Let's just go back a minute. Too many letters. I'm sorry for so many letters, but that's just the way it is. Lz, or the state M, was defined to be an eigenvector of Lz. That's what this says. In particular, the top eigenvector here, we can just substitute for M, we substitute L. So here we have it. Lz on L is just the numerical number L on L. What about Lz squared? It's just L squared. You're just hitting it with the operator Lz twice. The first time you hit it, it gives you an L. The second time you hit it, it gives you another L. So that's L squared. Okay, that was easy, but what about this here guy? What are we going to do about it? It's 0. Why? Because L plus, when it hits the top, runs out of states. That was the definition of the top here. The definition of the top state is that L plus gives 0. So we can just erase this. And now we've learned something, that this state L is an eigenvector of the square of the angular momentum. Let's write it this way. Let's write it down. L squared plus L times L. Or better yet, L times L plus 1. Just to remind you where it came from, an L squared came from here, and an L came from here. L squared plus L is L times L plus 1. So what do we find? We find out that the states in this multiplet here, the top state there, the highest state there, has an eigenvalue of L squared, which is L times L plus 1. The square of the angular momentum for that state is not little l squared. It's almost just little l squared. There's a little quantum correction here. If we were doing classical mechanics, we would expect that the square of the angular momentum would just be the square of the angular momentum about the z-axis for the top state there. Incidentally, the highest state is like the state rotating about the z-axis where all of the angular momentum is in the vertical direction. That's why it has the highest value. Any other direction it would be smaller. Okay, so we find a little surprise. It's not just L squared, it's L times L plus 1. But then there's another surprise, and this is a nice little exercise for you to do yourself. It's very easy, but I'll let you work it out yourself. Every one of these states in this same multiplet have exactly the same value of L squared. They all have the same magnitude for the square of the angular momentum. Basically what this multiplet is it's a quantum mechanical version of a state with a given angular momentum except in any possible direction. They all have the same L squared, the same square of the angular momentum, but they have different projections onto the z-axis. What's new in quantum mechanics is that the projection onto the z-axis is quantized. Comes in integer multiples. Okay, so that's what we know about angular momentum.
Question?
Yeah.
Could you state a little bit more? I don't understand the words that you said in terms of the little exercise where you did it.
Oh, okay, good. Yeah. Here's the exercise. Okay. Well, that's good. What we've shown is that L squared on the maximum eigenvector is equal to L times L plus 1 on L. In other words, that this eigenvector here happens also to be an eigenvector of the square of the angular momentum. Next step, I would like to show that L minus 1 also equals L times L plus 1 times L minus 1. In other words, that the next state down has exactly the same value for L squared. Okay? How do you do that? Well, you say start with L squared, and now hit this with L minus on L. L minus on L is the state L minus 1. And we want to prove that's equal to L times L plus 1 times L minus on L. That's the thing you want to prove. Okay. Can anybody guess how to prove it? Does the algebra here suggest anything? I'll tell you what it suggests to me. It suggests to me that we figure out what the commutator of L squared with L minus is. Imagine we discovered a marvelous fact, which I'm not telling you is true. It's true, though. That L squared and L minus commute. Supposing we discovered that. Then I could say that this was also equal, we're trying to prove this relationship. I would then say that this is equal to L minus times L squared L, right? But what's L squared on L? Let's see, what do we want to do here? If this commutes with this, we can push this through here. That's then equal to L times L plus 1. Yeah, we would have proved this relationship. We would have proved this relationship. We would have proved that this is equal to L minus times L plus 1 L, which is exactly what this says. So if we can prove that L squared commutes with L minus, then we can prove that the state L plus 1 is also an eigenvector of L squared. What about L minus 2? What about the next state down? Same thing. We just go down till we run out of states. Here's the exercise. The exercise is to prove that L squared commutes with any one of the components of angular momentum. Let's call it L sub I. Lx, Ly, L0. If it commutes with any of the components, then it will certainly commute with L plus and L minus. L plus and L minus is just Lx plus I or plus or minus ILy. So there's an exercise. Prove that L squared commutes with any one of the L's. All right, so here's what we found from the things that I showed you, plus the little exercise that you can do yourself, is that when you find a multiplet like this, going from L to minus L, such that there's no more above it and no more below it, you found not only eigenvectors of Lz, eigenvectors for which Lz is equal to m, but you've also found eigenvectors of the square of the angular momentum with eigenvalue L times L plus 1, where L is just the maximum value of m. So, for each one of these little L's, there are 2L plus 1 states, and they all have the same squared angular momentum. Roughly speaking, they have the same squared angular momentum because they're just tilts away from the vertical axis. That's a rough statement. That's quantum mechanically, it's a little trickier than that. But that's the classical analog, that by rotating and changing the z component of the angular momentum, you haven't changed L squared. Okay, so that's what we know about angular momentum multiplets. Yeah.
Can you raise the board to show your factorization? So when you factored Lx squared plus Ly squared, you could have just as fairly gotten L plus L minus as the operator.
And then I would have had the opposite sign here. Yeah, it would have given you exactly the same thing. If you had the L minus to the right, you would want to hit it on the lowest state instead of the highest state, but the sign of this would change. It would all work out. All work out the same way. It's a good question, but okay. So what we found is that there are collections of functions of the angles these eigenvectors are functions. They're functions of the angles. Why? Because rotation only affects the angular dependence. They're functions, and what characterizes them? A value of m, the eigenvector of Lz. So whatever they are, they're functions which have a little subscript m, and that's the z component, but they're also eigenvectors of L squared, or in other words, they can be characterized by a little L. And they're called YLM, and they're functions of theta and phi. You know what these things are called? YLMs of theta and phi? Spherical harmonics. They're functions on a unit sphere, functions of theta and phi, and they're the analogs on the sphere of e to the plus or minus IL theta. IL theta. They're the three-dimensional analogs. This is the two-dimensional functions. Strictly speaking, these are functions on a circle, so they're one-dimensional functions. But think of them as functions for a two-dimensional problem. These are the corresponding functions for the three-dimensional problem. And we don't really care very much about exactly what they are. We're going to finesse exactly what they are. We're never going to really need it. We could figure out what these functions are, but we're never going to need it. All we ever have to really know is that for every little value of L, There are 2L plus 1 of them. The 2L plus 1 of them have magnetic quantum numbers, m, that range from 0 to L and to minus L, and that the square of the angular momentum is L times L plus 1. That's all we're ever going to have to really know. To do atomic physics. Okay, any questions about the structure of angular momentum multiplets? And they all have the same energy. They all have the same energy, and the reason is because the angular momentum commutes with the Hamiltonian. That means when you apply L to a function, it doesn't change the energy. So they all have the same energy, at least for a problem of a central force. For central force, the angular momentum commutes with the Hamiltonian, and that's enough to prove that all of these have the same energy. Okay. No questions? We'll move on. In fact, let's move now to the central force problem. Now, I'm not going to take you through all of the manipulations involving partial derivatives all over the place with respect to theta and phi and so forth. We're going to do this by using a little bit of intuition from classical physics and work out with a tiny bit of cheating. The cheating is going to be to use classical physics to make a guess or two. But the guesses are well motivated, and we can do this rigorously. What is it we want to do? We want to solve the Schrödinger equation for a problem with a Hamiltonian, which is p squared over 2m. Now, p stands for the three components of momentum. So it's a vector, p squared over 2m, kinetic energy, plus some potential energy which only depends on the radius. Central force problem. Later we'll be specific about what central force problem. Of course, what we're going to think about is the coulomb force. But for the moment, let's not specialize. And let's do classical physics first. Okay, first statement. The angular momentum is conserved. Now, you could check it. You could work it out by working out the equations of motion and seeing that the angular momentum is conserved. You can also just say angular momentum is conserved whenever you have rotational symmetry, and that's correct. It's the same statement as saying that you have momentum conservation whenever you have translation invariance. It's Noether's theorem. Classically, quantum... Heavy scone. That's a good scone, man. All right, so let's believe angular momentum is conserved. Angular momentum is a vector, r cross p. It's conserved. That means its magnitude is conserved, but also its direction is conserved. And that means, as I said before, that the plane of the orbit is also conserved. So once we know the plane of the orbit is also conserved and that everything is rotationally symmetric, we might as well classically put this whole thing in the xy plane. So there's our orbit. Orbits do not have to be circles. Most orbits are not circles. In fact, for a general problem, most orbits won't even be closed. If you take a general potential, most orbits will not be closed. They will They will precess about, the axis of the orbit will precess. We're not going to worry too much about whether the orbits are closed. It's not our concern right now. Now, next, let's look at an orbit. Here's R. And let's put the momentum over here. The momentum is along some direction. It's in the plane because we know that the motion is in a plane. So it's in the plane, and it's pointing in some direction. It may or may not be perpendicular to R. In fact, it could even be, the velocity could be along R. There are orbits, for example, which just go back and forth through the origin. So there's no rule that says that the momentum is perpendicular to R. There is a rule that says the angular momentum is perpendicular to both R and momentum, but we're finished with that. Okay, let's take the momentum vector and decompose it into an angular part, let's call it the theta component, p theta, and a r component. So the momentum has two components, one along the angular direction and one along the r direction. What about p squared? P squared is the sum of the squares of both of them. So h is pr squared plus p theta squared over 2m. And that's it. But what about the angular momentum, the magnitude of the angular momentum? The magnitude of the angular momentum is p theta times r. Is that clear to you? That p theta times r is the angular momentum. R cross p. R cross p, the magnitude of it, is the magnitude of r times the magnitude of p theta. So the magnitude of the angular momentum is equal to p theta times r, everybody magnitude. P theta times r. Or another way to write it is that first of all, L squared is equal to p theta squared times r squared. And now let's write p theta squared is L squared over r squared. That was easy. And let's stick it into the Hamiltonian. PR squared plus p theta, oh, this is not, I'm sorry, you didn't correct me, plus v of r. Okay, PR squared, well, that's just PR squared. H is PR squared over 2m. But what about p theta squared? P theta squared is L squared divided by r squared plus v of r. Let's erase all of this now. Look at what we have. We have a problem which for all practical purposes could be thought of as a problem in one dimension, namely the radial direction, pr squared, plus a potential energy v of r, plus another term in the potential energy. Remember that L is conserved. So once you pick L, once you know what the angular momentum is, it doesn't change on you. So once you know what it is, you can freeze it. And you can say the Hamiltonian of this system is just pr squared as though it was just a one-dimensional problem, plus an extra term which goes like 1 over r squared, plus the original v of r. What is this term called? Physically, what is it? Is it attractive or is it repulsive? How do you tell whether it's attractive or repulsive?
It's attractive.
Why do you think it's attractive? Potential energy. 1 over r squared gets bigger as you move away. So, sorry, r squared gets bigger as you move away. 1 over r squared decreases as you move away. So which way is this force pushing you? Forces push you towards smaller energy. Forces always push you toward smaller energy. That's why they're minus the derivative of the potential with respect to position. This is pushing you away from the origin. What kind of thing is this, pushing you away from the origin? There was nothing in this problem that pushed you away from the origin. What is it? Yeah, sure. It's centrifugal force. Or this is the potential energy that's associated with the centrifugal force. And it gets very big when r gets small. When r gets small, for fixed angular momentum, it really repels you away from the origin. And so if an object comes in with a given amount of angular momentum, it can't get very close to the origin. What it does is swing around the origin. Okay, so this is what keeps the particle from getting to the origin, and it is the centrifugal force. There's only one situation where it's not there. When is it not there? For L equals 0, right? For L equals 0. And then for L equals 0, we're talking about an orbit which just goes through the origin, back and forth through the origin. It has no angular momentum, and this term isn't there. But as long as there's any angular momentum, then it can't get to the origin because there's this huge repulsion effect. It's not a real repulsion, it's the centrifugal force, but it's there. P of r, what about P of r? That's just the momentum associated with the r direction. Okay. Let's go a little bit more with the classical physics. Let's plot this effective potential energy. This becomes the effective potential energy for the one-dimensional problem. It has the ordinary potential energy plus the centrifugal barrier. This is called the centrifugal barrier, and it looks like this. Let's suppose V of r is attractive. For example, it could be the attraction of the electron to the proton. Then V of r would look something like that. Well, let's do it a little better. V of r would be negative because it's attraction, and it would be 1 over r, so it would look something like this. Now, that's V of r. What about L squared over R squared? Well, depending on L, whether or not, for any L except L equals 0, it's going to blow up at the origin like 1 over R squared and then fall quickly to 0. In fact, if V of R is the Coulomb potential, it goes like 1 over R. It falls more slowly than the centrifugal barrier. Centrifugal barrier falls very quickly to 0, 1 over R squared, and V over R a little more slowly. What does the combination of them look like? Well, the combination of them, which is dominant at small r? For small r, which one is bigger? 1 over R squared or 1 over R? 1 over R squared is much bigger. So, very close to the origin, this is the dominant thing. What about for large r, if V is 1 over R? Supposing V is the Coulomb potential. 1 over R is bigger than 1 over R squared. So, asymptotically far out, the Coulomb potential wins. And what happens in between? What happens in between looks like this. Yeah. Okay, so what kind of motions do you have? We have an effective problem which is completely one-dimensional now. It only depends on the r-axis. And all of the angular story is fixed by the angular momentum. So once you know the angular momentum, it becomes a one-dimensional problem. What do you think motion in this kind of potential looks like? Well, the simplest kind of orbit, or the simplest kind of motion, would just be equilibrium down at the bottom of the potential. That's an orbit in which r doesn't change. It's a circular orbit. Okay, that's a circular orbit. What other kind of orbits can you have? Well, what other kind of motions could you have in a potential which looks like this? Basically, you can have oscillations back and forth. Oscillations which go back and forth take the particle from a minimum distance from the origin to a maximum and back again. So these are orbits which go from a minimum distance to a maximum distance and back again. For the Coulomb potential, they would be the elliptical orbits. Right. And that's the classical physics. In a nutshell, that's the classical physics. What about the quantum physics? For the quantum physics, we have a wave function. And the wave function, instead of, we don't have a particle position, we don't have a momentum, we have a wave function. And the wave function is psi of r and also angles. But the angular structure is totally taken into account by knowing the angular momentum. If we know the angular momentum, then we know that the angular part of the wave function is just one of these spherical harmonics, which I've erased, but that's gone. But we don't have to worry about it. It's a one-dimensional problem, psi of r, and what does it satisfy? It satisfies the Schrödinger equation that h on psi of r, let's say the time-independent Schrödinger equation. What is the time-independent Schrödinger equation? What do you put on the right-hand side? The energy. And it determines the eigenvalues and the eigenvectors of energy. Now what is h? H begins with PR squared. What is PR? PR is, of course, I h bar d by dr. As always, in quantum mechanics, a component of the momentum is I h bar times derivative with respect to the corresponding coordinate. So, PR squared. Here's PR squared. PR squared is going to equal minus, because of two factors of I, h bar squared, I'm putting in the h bars now, second derivative with respect to r. That's the first term in the Hamiltonian. I left something out. I left out twice the mass. Whose mass might I be talking about, incidentally? The planet Mercury? More likely the electron for this discussion, but it could be the planet Mercury too. I don't think we would bother doing quantum mechanics then. d second by dr squared. That's the first term in the Hamiltonian. The second term in the Hamiltonian is exactly what's written there, plus 1 over 2m L squared over R squared. But what is L squared? Now we come back to here. L squared is not little l squared, it's L times L plus 1. Why? Because this is the square of the angular momentum. What appeared there was the square, it was Lx squared plus Ly squared plus Lz squared. And so this becomes L times L plus 1 over R squared. That's one of the effects of quantum mechanics, just to change L squared to L times L plus 1. And finally, plus V of R. V of R. And you can plug in your favorite potential into there. What do we do with it? We act on psi. And psi is now a function of R, psi of R, psi of R, psi of R equals E psi of R. And that's our Schrödinger equation. The solutions of that equation are the eigenvectors of energy with given angular momentum, and the eigenvalues are the energy levels. I have a feeling I left out some h bar squares in here. I probably did, because where did it come from? It came from p theta squared. It's probably an h bar squared in here too, if you track it. I think. Yeah. Yes. All right, that's what we would like to solve. We'd like to solve this, find the energy levels of an atom. We would like to find the wave functions of an atom. We'd like to know what the electron probability distribution is like, and so forth. Okay, so we're not going to do that. We're not going to do it because it's just a matter of solving differential equations, and this is not a course in differential equations. But we can still sort of scout it out. And, yeah.
For a given L, I think what you said earlier suggests that they would have the same energy level.
Say it again.
That all the eigenvalues would give you the same energy level.
Yeah, all of these levels here, the 2L plus 1 of them, have the same value of little l, and therefore the same energy.
Oh, okay.
Yeah.
So you were able to replace L squared with L plus 1 because psi is a linear combination of the m's?
What's this?
But that applies to any value of L, we said, right?
Yeah, so if we know the angular momentum, quantum number of the wave function, then we can plug it in.
What L is really is the maximum eigenvalue.
It's the maximum eigenvalue for that multiplet.
Yeah.
There are wave functions of any angular momentum, but they come in these, the pattern is that they come in these 2L plus 1 multiplets. The 2L plus 1 multiplets are the quantum mechanical analog of you find a wave function and you rotate it around. Right. This tells you what the energy levels associated with a given L are. And then you want to solve it. Okay, too hard to solve for most potentials. Most potentials you write down, you'd have to solve it numerically. The Coulomb potential happens to be solvable. If you want to solve it, the solutions to this equation are called Gegenbauer polynomials or Gegenbauer functions. Good luck. Look up Gegenbauer functions. You will learn very little from it. I used to know what a Gegenbauer polynomial is. I do not anymore. Okay. Let's look at the effective potential. What we're doing is we're solving a Schrödinger equation in a potential which looks like this. We're solving the Schrödinger equation for a problem which effectively has a potential energy which looks like this. And we want to know what kind of wave functions and what kind of energy levels will it be. Okay. If you know anything about solving Schrödinger equations, then you know that given L, with given L, in other words, we're given the potential, you know that first of all, typically there are more than one bound state. A bound state is a state which is confined with a wave function which doesn't leak out too far. They correspond to discrete energy levels. And you know that the thing which characterizes the energy level is the number of nodes in the wave function. Does everybody know what a node is? A wave function which is never zero, let's say it's always positive, has no nodes. If it goes up, goes down, passes through the origin, and then it has one node. So here are some functions with different numbers of nodes. Here's a function with no nodes. Here's a function with one node. How about a function with two nodes? A function with two nodes goes up, comes down, goes back up, and comes back down. The number of nodes are what characterize the different energy levels of a solution to the Schrödinger equation. The more nodes, the higher the energy. Why would it be that the more nodes, the higher the energy? What's that? Yeah. Something like that. Yeah. The more nodes, the faster it wiggles. The faster it wiggles, the larger the momentum. Momentum is characterized by wiggles. The wave functions of momentum states wiggle. The higher the momentum, the faster they wiggle. The more they wiggle, the more nodes they're going to have. So generally speaking, it's a theorem. It's actually not, it's a theorem. The lowest energy state in a given potential has no nodes. The first excited state has one node. The next excited state has two nodes. Eventually, you may or may not run out of solutions, but they're ordered according to the number of nodes. So let's start. Let's see now what we can say about the spectrum of an atom. It doesn't have to be a realistic atom. This could be an atom with 1 over r potential, like a realistic atom. It could be 1 over square root of r. It could be e to the minus r, but some potential. What can we say? Let's see if we can organize the energy levels and the states of the atom. Okay, let's see how I did this. Yeah, let's plot horizontally the different angular momenta. The little l's. Little l. L equals 0. 0. L equals 1. L equals 2. L equals 3, and so forth. Now, each one of these L's has its own Schrödinger equation. Remember, the Schrödinger equation involves L as a parameter. So each L may have several bound states, several solutions. Let's take L equals 0. L equals 0 will have a lowest energy state. Let's see, what are we plotting here? Let's plot energy vertically. Okay, there'll be the lowest energy level. It has no nodes, and L equals 0. So it's someplace over here. Okay. What's the next state with L equals 0? The next state with L equals 0 has a node in it. Same potential, one node. So it's up here over somewheres. How many states are there for L equals 0? Each case has one state. L times L plus 1 is 1 when L is equal to 0. Is that right? No. No. 2L plus 1 is 2L plus 1 is right. 2L plus 1 is 1. So every one of the states with L equals 0, 1 node, 2 nodes, 3 nodes, and 4 node, they all have one state associated with them, and they're not equally spaced. They are whatever they are. Whatever they are. Okay. Those are the energy levels with 0 angular momentum. Now let's go to angular momentum 1. At angular momentum 1, there is also a state with no nodes. We solve the same Schrödinger equation except with L equals 1 here. L times L plus 1 when L is equal to 1. 1 times 2 is 2, right? 1 times 2 is 2. On the other hand, for L equals 0, this was 0. Okay, so same Schrödinger equation, different value of L. At L equals 1, we will also find things with one node. Will their energy be larger or smaller than the L equals 0 state with no node? Just a wild guess. Yeah, it's got angular momentum. It's swinging around there. It's got angular momentum. And besides which, this is a positive term in the Hamiltonian. So how could it possibly lower the energy? And it can't. So the L equals 1 state with no nodes will lie somewhat above the corresponding state with L equals 0. Likewise, the state with 2 nodes, this one lies above this one, will lie above this one. And just by virtue, the whole spectrum may move over, but it will move up a little bit because the angular momentum is higher. How many states are there at each one of these levels? I've drawn a little dash here to indicate a possible energy level, an energy level. But what is its degeneracy? How many states are there at each one of those dashes? 2L plus 1, 3. So we should really draw these as 3 little dashes if I was trying to separate them and indicate 3 states. Each one of these is a triplet. Okay. What about at L equals 2? At L equals 2, we've put in a little more angular momentum. Surely we've raised the energy again, and in fact we will have. How many states will there be for each state at L equals 2? 5, 2L plus 1. So when we go up to L equals 2, let's move them over a little bit, L equals 2, we'll go up a little bit, and we'll have 5 states. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And so it goes. L equals 3, 2L plus 1, let's see, 3 times 2 is 6, 7 states, and so forth. And that's about what it looks like. That's about what the general solution looks like for a sort of arbitrary potential. At some point, when the energy gets too high, just like in classical physics, what happens when the energy gets too high for an orbit around the sun? It escapes. It exceeds escape velocity, and it's no longer bound to the sun. Likewise, when the energy gets too high, the electron escapes, and so there's a bound to the energy up here. No states above there are actually bound. So all the bound states have basically negative energy. The energy goes negative down here. And this is what the spectrum of anything in essential force looks like. The Coulomb potential has a very special feature. It's almost accidental. It's not exact. It is an exact statement about the non-relativistic Coulomb potential, but it is not an exact statement about atoms, the statement I'm going to tell you. It's violated by every possible correction to the simplest theory of the atom. It's violated by the finite size of the nucleus. It's violated by relativistic corrections. It's violated by the fact that the electron has a spin which couples to the orbital. Everything on Earth violates it. So it's something of an accident. It's very special to the Coulomb force. And it goes as follows. The first level here, which is moved up a little bit, this is the 0 node state. The 0 node state for L equals 1 happens to have exactly the same energy as the 1 node state for L equals 0. Here's the 1 node state for L equals 0. The 0 node state, the first one that occurs for L equals 1, occurs at exactly the same energy as the 1 node state for L equals 0. That's a mouthful. What about the 2 node state? The 1 node state of L equals 1 occurs at the same energy as the 2 node state of L equals 0. Exactly the same. Exactly the same for the simple Coulomb force. And so on and so forth. This is a pattern. Now you go to L equals 2. The L equals 2 0 node state, in other words, the lowest L equals 2 state, has exactly the same energy as, which is this now? This is no node, 1 node, 2 nodes. It's up here, and there are 5 states. 1, 2, 3, 4, 5. What about the L equals 3? The L equals 3 begins up here, 7 states. 1, 2, 3, 4, 5, 6, 7, and so forth. That's the pattern, and it's an accident. It's not completely an accident. Nothing in mathematics is ever an accident. But you can say things are accidental when, you know, just small changes in the potential or small changes in anything ruin it. And this, in that sense, is an accident. I'm not going to prove it. It sounds like an extra symmetry law. It sounds like extra degeneracy. It sounds like there are degeneracies between states. It is a symmetry, but it's a rather bizarre one. It's a rather bizarre one that you would never notice if you were thinking about this. As I said, it's very special to the Coulomb potential and is not exact, so I think we won't bother proving it. It's a nuisance to prove. But it is a fact. It's a very special fact about the special 1 over r potential. So there it is. That's the spectrum. What is the degeneracy at each level? Here's the lowest energy level. There's only one state. It has angular momentum 0. It's called the ground state. It's the lowest energy state of the atom. If this were the hydrogen atom, for example, it would be the most deeply bound state. Then you go up one level. You go to the first node of the 0 angular momentum state, or no nodes for the angular momentum. And how many states do you get? This is 1. This is 4. How about the next one up? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 states at the next level. Anybody want to guess what the next one is? 16 is right. So for the Coulomb potential, the states are degenerate like this, and the degeneracy is always the square of some integer.
When you say the Coulomb level, do you mean the atom, or you just about
The atom, the hydrogen atom, approximately satisfies this. It's a very good approximation, but all kinds of things violate it. Relativistic corrections, and as I said, just the finite size of the nucleus is enough to disturb this. Now, the nucleus is very, very small. Why does the finite size of the nucleus disturb it? The nucleus is a little ball of charge. We've pretended the charge was a point at the center. Okay? That would give us exactly the Coulomb potential. If the charge were distributed over a little ball, the potential energy would be slightly different than the exact Coulomb, especially when you get into the nucleus. The electron can pass through the nucleus. It's just a ball of charge. The nucleus is just a ball of charge. The electron is repelled, it's attracted to the nucleus, and it can pass through the nucleus. When it passes through the nucleus, it senses the fact that the charge distribution is not the perfect 1 over r squared, 1 over r potential. If the potential is anything but 1 over r, this degeneracy fails. So because the nucleus has a finite size, there's a very, very slight deviation away from this. Now, the nucleus is 100,000 times smaller than the size of the atomic wave functions. So the nucleus is very small, and this is a very negligible effect. But the only point is just that this is something of an accident and not particularly deep. I don't know anything deep about it. The fact that it has this kind of degeneracy. And that's your spectrum of the hydrogen atom. That's the spectrum of the hydrogen atom in the idealized approximation, non-relativistic, perfect Coulomb potential. Okay. One state, the ground state. 4 states above it. 9 states above that. Is that the way real atoms work? No, it's not the way real atoms work. Real atoms have 2 degenerate ground states, 8 first excited states, 18 next excited states, 32 next excited states. And so there's something missing in this analysis by a factor of 2. Spin. Yeah. Spin. Right. So we haven't talked about spin, and I think we won't tonight. That's all of this is, of course, just trickery for solving the Schrödinger equation. Let me write the Schrödinger equation in its original form before we went to angular variables. It wouldn't be particularly helpful to try to solve it, but we might just try to write it down. P squared means px squared plus py squared plus pz squared. It can also mean pr squared plus p theta squared. But it means px squared plus py. So this really means minus, what is it, h bar squared d second with respect to x squared plus d second with respect to y squared plus d second with respect to z squared of psi plus v of r times psi equals e psi. That's the equation we really set out to solve. You solve it by going first to polar coordinates or radial coordinates, radial and angular coordinates, and then using the algebra of the angular momentum to deal with the angular parts of it. And it's very simple. The angular parts of it are all subsumed by saying you work with angular momentum eigenstates. L squared is the thing that comes in, and L squared is nothing but L times L plus 1. By that time, you're down to a one-dimensional Schrödinger equation, and you use whatever mathematical strategy you know for solving such things. Once you get it down to one direction, it's just an ordinary differential equation. It's not even a partial differential equation. You only have derivatives with respect to r. So at worst, it's a numerical problem.
Good question.
Yeah.
First is the difference between the idealized Coulomb law
Yeah.
and what you measure. Could that be a way of determining the size of the nucleus?
No, there are too many corrections which are much bigger. No. I just point out the nuclear size because it's an easy one to think about, but it's minuscule. No.
And the second question is, you get back to the very beginning between classical mechanics and quantum mechanics. The biggest difference is capital L squared is equal to little l squared in classical, and it's equal to L times L minus 1 in quantum.
What's that? What's L times?
Capital L squared is equal to little l squared times little l squared plus 1. Right?
No.
Right there.
Big L squared is L times L plus 1.
Yeah. I just said it wrong.
Yeah.
And that difference is caused by the fact that the things don't commute.
Yeah. Mm-hmm. It's, in other words, it's a little quantum correction.
Okay, right. That's
Right.
right.
Right. It's a little quantum correction. Yeah. Yeah.
Do wave functions have compact support?
No, they're spread, but they fall off very rapidly as you move away from. Compact support would literally mean they go to zero outside a certain distance. The statement that the wave function has compact support would mean that it's zero out past a certain point. But it's exponentially small. Like they decrease exponentially. So for practical purposes, if you go out sort of past a certain distance, each wave function becomes negligibly small. Does that answer your question?
Yeah, but there is some non-zero probability you can find something
Arbitrarily far away, but it goes to zero exponentially with distance. Right.
Question?
Yeah.
When L is 0, little l,
Yeah.
the shape is not like this, it's just the Coulomb potential, right?
Oh yeah. Good. That's right. For when L, that's right. When L is 0, then there's no centrifugal barrier. Right.
So what is the meaning of the stable point in this case?
You mean the point at the origin?
No, before it was in this well.
Okay.
Now the well is gone.
Yeah, that's right. That's right. So classically, it would just go to the center. It would just go to the center and sit at the center. Quantum mechanically, it can't both sit at the center and it would go to the center, not only go to the center, but it would be at rest at the center. The state of lowest energy would be at the center, where it would have negative infinite energy, You would lower the potential energy by getting to the center, and you would lower the potential energy by making the momentum zero. You can't have both. You can't have the momentum and the position definite. There's a compromise, and the compromise is for the wave function to have a little bit of spread away from the origin here. The Schrödinger equation has a solution, and the solution has some sort of exponential tail, but it's concentrated near the center. It's the uncertainty principle which prevents it from sitting literally at the center. Yeah. Yeah.
You motivated Hamiltonian from classical mechanics.
Yeah, we certainly did.
Was that the trick you used to make
For
the lack of rigor? I mean, it was one.
no. Okay. This is motivated by classical mechanics up to here. Okay? But classical mechanics motivated p squared over 2m, where p was a vector, and allowed us to write this down. Once we write this down, we have a very, very precise quantum mechanical problem, an exact Schrödinger equation. I did a little bit of guesswork in going from here to here. Classically, it's completely rigorous to go from px squared plus py squared plus pz squared to go to pr squared plus p theta squared. You have to justify the step quantum mechanically. All right, but that's something that would take an hour at the blackboard, and you wouldn't learn very much from it.
Another question, if I may, please. You have z there, which implies 3 dimensions, but you said you reduced it to 2 dimensions by going only r and theta.
Classically. Quantum mechanically, the wave function fills up 3 dimensions. Every wave function fills up 3 dimensions. Classically, and the trick is to say angular momentum is conserved. That means the plane of the orbit is conserved. Just change coordinates so your xy plane is in the plane of the orbit. Can't do that quantum mechanically.
But you did it.
No, I didn't. No, I didn't. But the fact that you can't do it, believe it or not, is just a statement that L squared is replaced by L times L plus 1. Yeah. It's these other LXs and LYs creeping into, yeah. If you could just put in for L squared, LZ squared, then it would just be little L squared. The fact that it's 3-dimensional comes back at you just from the L times L plus 1, yeah.
This is more, I think, what you'll do with the harmonic oscillator. But is there always a raising and lowering operator looking at that?
No, only when you're very lucky. And I would say basically physics has been lucky this way twice. But however, the harmonic oscillator piece of luck is very pervasive. Almost everything in nature can be well approximated, or many things in nature can be approximated by harmonic oscillators. For example, even the not L equals 0, but go to the higher angular momentum states. In the higher angular momentum states, the potential looks like this. And there are orbits which oscillate back and forth at the bottom here. And the simplest approximation to those orbits is to treat them as a harmonic oscillator. So there's all kinds of places where there are harmonic oscillators, and because of that, the trick of whatever trickery goes into the harmonic oscillator is very pervasive. But there are not many mathematical cases where raising and lowering operators, or sometimes they're called ladder operators, only when you're very lucky. Okay, that does it for atoms for the moment. We're going to come back to atoms. We're going to talk about spin. We're going to talk about the fact that the electron is a fermion instead of a boson, and how that determines atomic structure a little bit, and how atoms radiate and give off photons. All that stuff we'll come back to. But let's forget atoms for the time being and come to the harmonic oscillator. As I said, everything in physics which has an equilibrium, if you disturb the equilibrium a little bit, chances are it's going to behave like a harmonic oscillator. So it's a very pervasive thing. And the model for it is just a particle or a weight on the end of a spring. We're going to simplify it a little bit. Some of the parameters aren't terribly important. Well, imagine a weight hanging by a spring. It has an equilibrium position, and the deviation from the equilibrium position, not the deviation from where it's hanging, but the deviation from the equilibrium position, we'll call that x. I'm going to take the mass of the weight to be 1. Now we can redo it for other masses. It doesn't, it's a little exercise to do it, but you won't, there's nothing new. Nothing new happens. So the mass is 1, and the spring constant K is the standard terminology for a spring constant, we'll call omega squared. We're going to find out in a moment that omega is the frequency of oscillation. Okay. But the spring constant is omega squared. What is the energy of a classical oscillator? The energy, let's call it, let's give it its name, the Hamiltonian. The Hamiltonian is the usual p squared. Now p is one-dimensional. It's just a momentum, the x momentum, p squared over 2m. That means p squared over 2. M has been set equal to 1, plus k omega squared, x squared over 2. Let's work out, let's just check that this is right. What we're going to do is work out the Hamilton equations of motion. If you don't remember Hamilton's equations of motion, it's okay, I'll tell you. Hamilton's equations of motion are dH by dP equals x dot, and dH by dx equals minus p dot. How many people remember minus p dot? Thank you. Everybody remember that? Of course you do. Okay, let's check. Let's see what we get. dH by dP is equal to x dot. dH by dP is p. So this says that p equals x dot, right? That's not too bad. Momentum is equal to velocity. What happened to the mass? Oh, I set the mass equal to 1. So that's okay. It's all right. I'm a physicist. I'm allowed to do that. P is equal to x dot. That's good. Now, what about dH by dx? dH by dx is omega squared x plus or minus? Minus. Okay, let's check Newton's equations. Let's calculate the acceleration. The acceleration is x double dot. That's p dot. But p dot is equal to p dot. Do I have the sign wrong here? The h by dx equals minus p dot equals plus omega x squared. The h by dx is plus omega x squared. So x double dot is equal to minus omega squared x. X double dot is minus omega squared x. That's the equation of an oscillator with frequency omega. Okay, everybody recognize it? X double dot is minus omega squared x. Acceleration, m was set equal to 1. Acceleration is equal to restoring force with, as I said, k is equal to omega squared. Okay, so this is the right Hamiltonian for the harmonic oscillator. And now what we want to do is find all its energy levels, eigenvectors, and find out what it does, quantum mechanically. Classically, we know what it does. It swings back and forth with frequency omega. Okay, let's see what we can do with it. It's the sum of squares. What do you do with the sum of squares? You factor it. Everybody knows that you factor the sum of squares. Well, not everybody knows that. Dirac knew it. All right, so let's write, first of all, a 1/2 downstairs. And let's write p plus I omega x times p minus I omega x. Is this looking familiar? Not from the harmonic oscillator, but from about an hour ago. Lx plus ILy and Lx minus ILy. Yeah, okay. So let's do this. Is this right? Yeah, that's right. I'm also going to put, I'm going to put an omega downstairs and an omega upstairs. Only because it's convention. Okay. Now, let me not put those omegas. I'll do that later. Is this right quantum mechanically?
Correction.
No, because there's a term p times x and x times p, but they don't cancel because x and p don't commute. So let's see. So what do I have to subtract here? I have to subtract minus 1/2 from here. And then I will have I. Now we have omega. We have x times p minus p times x. X times p minus p times x, and I think I have it right. I've subtracted it because it was appearing in here in an unwanted way. So I've subtracted it, and now I use one more thing. This is the commutator of x and p. What's the commutator of x and p? I. I've dropped h bars all over the place. We'll put back the h bars later. Okay, xp minus px, that's I. Commutator of p of x with p equals I. Strictly I h bar if I wanted to keep the
Why is that true? Why is that true?
You don't remember that?
No.
From 2 years ago?
Okay, I'll look back my notes.
That's the basic canonical commutation relations of a coordinate and its corresponding momentum.
Yeah,
We-
that's the
we use the-
one-dimensional case.
Hmm?
That's the one-dimensional case. If there-
Yeah, one-dimensional case.
It's not px,
No.
then you have a problem.
Why?
Then it'll be 0.
X commutes with P, Y, and P, Z.
Yeah, so
Yeah. This is x and px. There's only one coordinate in this problem.
that's what I'm saying.
Yeah.
That's the one-dimensional case. If you had the other dimensions, you would have to clarify.
If you had other dimensions, you'd have to worry about them. You don't. Okay, this is the one-dimensional harmonic oscillator. So what is xp minus px? All right, let's keep the h bar around for a second. We'll keep the h bar around for a second. Later on, we'll drop it. But it's I h bar minus I times I is plus I. So this becomes plus h bar omega over 2. Okay, this is a constant. This is a constant. What's it called? It's got a name. It's called the 0-point energy. Okay. It's there even when the harmonic oscillator is in its ground state. We're going to see that. even in its ground state, where this is 0, everything else is 0, this still remains. Why is there a ground state energy? Let's ask, why does a harmonic oscillator have a ground state energy? Why isn't the energy 0? What's the energy of the ground state classically? 0. How does it get to be 0? Well, the ground state is just the oscillator at rest, p equals 0, at position 0. Both of these are 0. Quantum mechanically, you can't have both x and p be 0 simultaneously. Furthermore, both of these are positive, and therefore they can't cancel each other, so there's got to be a little bit of energy in the ground state. It's the Heisenberg uncertainty principle, which tells you that you couldn't have had 0 energy in the ground state. Okay, but once you know that, here, the Hamiltonian is this thing over here plus a constant. Okay, the constant may or may not be important, but it's just an additive number. Every energy level has an extra h bar omega over 2. We're not going to lose anything terribly important if we drop it. I'm going to drop it, but later on we can come back and add it back in as an overall additive constant in the energy. Yeah.
Can you say anything further by the fact that it comes out to be positive instead of negative?
Okay, it couldn't have been negative because x squared plus p squared is positive. The energy is x squared plus p squared. That's a positive definite operator. It can't come out to be negative. All right. All right, so let's concentrate on this thing over here. Let's forget where it came from. We're forgetting where it came from. And we just want to know what's the properties of this operator. Here's a certain operator. It is the Hamiltonian, apart from this additive. I'm going to say it once more. There's an additive constant, and now I'm not going to say it again until I put it back eventually. But this is the Hamiltonian. Okay. And we want to understand what its spectrum is, what its eigenvectors are, what is its properties. We have two operators. It factorizes very nicely. It makes sense to give these operators names. And I'm going to do something just for future benefit. I'm going to put an omega up here, and I'm going to put a square root of omega down. Here's what we're going to do. We're going to put a square root of 2 omega downstairs and a square root of 2 omega downstairs here. You see what I did? I took the 2 that was downstairs and I split it between these two. And I took the omega, which I stuck upstairs, and split it between the two factors again. This is the standard way that even the classical harmonic oscillator is often written in this way. We need to give these guys names. P minus I omega x over square root of 2 omega, and P plus I omega x. Their role is going to be exactly the same as the raising and lowering operators in the angular momentum case. It's going to take us up and down a ladder. This time it'll be a ladder of energy levels, not a ladder of angular momentum. Okay, so let's give them names. A plus is equal to P plus I omega x over square root of 2 omega. And A minus is the same thing, but with a minus Ix over square root of 2 omega. They are Hermitian conjugates of each other. They're Hermitian conjugates of each other because one plus I omega x minus I omega x. And we can now write that the Hamiltonian is omega times A plus A minus. That is really simple, except who knows what's buried in the A plus and the A minus. It's a crappy looking thing for sure to have square roots of omega and square roots of 2, but it turns out not to be so crappy. Okay. What should we do with these A pluses and A minuses? What would Dirac do?
Find the eigenvalue.
Yeah, I do that, but he'd probably stare at it for a while and say, I can't figure out the eigenvalues. So he would commute them. He would commute them. He would say, what's their commutator? Here I have a Hamiltonian, which is A plus A minus. I don't know much about A plus and A minus, but let's figure out what their commutator is. I'm bored. I've got nothing else to do. I like to sit around and commute things. Okay, so let's take the commutator of A minus with A plus. Okay, that's going to be commutator of. Now, there's going to be a 2 omega downstairs, right? 2 omega downstairs, 1 over 2 omega. And then there's going to be the commutator of P minus I omega x with P plus I omega x. Now, who commutes with who here? Well, who doesn't commute with who? Who doesn't commute with whom? All right. P doesn't commute with X, and X doesn't commute with P. That's all. X commutes with X, and P commutes with P. So what do we have here? We have equals 1 over 2 omega. Now, we have an I omega. Let's take this. Let's take this one here first. Then we have a minus I omega from here. And then the commutator of X with P. What's the commutator of X with P? I. So that gives us an I. I times minus I is plus 1. We have an omega over omega. All together, this is just 1/2. But that was only one term. That was this commutator of this one with this one. The other one is the commutator of P with I omega x. It's exactly the same. If you work it out, you'll see it's exactly the same number. And so all together you get 2 of them, plus 1/2. And the commutator is 1. We now know 2 things. Turns out this is enough. This is really all you have to know. You can throw away everything else. The Hamiltonian is omega times A plus A minus. And the commutator of A minus with A plus is 1. There's one more fact here, and it's the fact that A plus and A minus are Hermitian conjugates of each other. That plays a role. Okay, good. Let's give this thing A plus A minus by itself a name. Let's call it capital N. It even gets simpler now. The commutator of H is omega times N. And the next step, of course, if we were Dirac, would be to start commuting N with A plus and N with A minus. It's a good thing to do. It's a good thing to do. You'll find out that the commutator algebra is very simple. But I don't think we have to do it. I think we can proceed without doing that. Let's see what we can learn. First of all, this N object is a Hermitian operator. If you take an operator times its own Hermitian conjugate, it's always Hermitian. That's something you can check. That means N has a complete set of eigenvectors. Well, of course N is Hermitian. It's basically, apart from the factor omega, it's the Hamiltonian. It started Hermitian, it stays Hermitian. So N is a Hermitian operator, and that means it has a complete set of eigenvalues and eigenvectors. What we want to do is find those eigenvalues and eigenvectors. Those eigenvalues and eigenvectors are the energy levels and eigenstates of the Hamiltonian. Okay, so let's see what we can learn. We want to find the eigenvalues of N. Once we know the eigenvalues of N, we know everything we want to know. So let's suppose that N has an eigenvector called little n, and that the eigenvalue is just little n. I haven't made any assumptions about whether little n is an integer or anything else. I've called it n because it is an integer, but we haven't proved that. Let's just call it little n. Big N is an operator. It's a plus a minus. Little n is an eigenvalue. This is the eigenvalue equation. Okay, and we can also write it in another way. We can write it a plus a minus on little n is little n times n. I've just written that big N is a plus a minus. Right. These two equations are the same thing. Now let's take the commutation relation here. Let's write it out. A minus a plus minus a plus a minus equals 1. But let's take this operator, this equation, and operate on the state n and see what we get. Right? You agree with this equation? It's just a commutation relation, a minus a plus a minus equals 1, but then,
Minus.
what's that?
A minus a plus a plus.
That's
Right, thank you.
No.
Yeah. Good. And let's multiply it. I'm looking at it, I'm staring at it, trying to figure out what to do with it. I know what I really want to do with it. What I want to do with it is I want to apply a plus. What I want to do is show that a plus will increase the energy. I want to show that a plus is a raising operator. So what I want to concentrate not on n, but on a plus times n. So I have to multiply it by a plus. This is my goal, to show that a plus times n is something interesting. That raising with this a plus operator does something interesting. Okay, so now we have an equation. Let's see what we get. First of all, we have a plus, a minus, a plus. That's the first term here on n. Now what about the second term? Minus a plus, what's a plus a minus on n? Right, so this is minus a plus minus n a plus times n. I've written that a plus a minus on n just gives me a numerical factor n. So that's this over here. I still have the a plus, and that's over here. And finally, on the right-hand side, I have a plus times n. Okay, let's shift this over to the right. What happens if I shift this over to the right? Here I have a plus times n, and here I have n times a plus times n. What do I get? N plus 1. Ooh, that's good. Let's see. This one got shifted over to the right. It gave me this n, and the other one gave me the 1. But what about this one over here? A plus times a minus is the operator capital N. This is the state that I'm interested in. So n on this state, a plus on n, let's put a circle around it, is equal to n plus 1 times that same state. So guess what I found? Pretty much what was expected, that the raising operator gives me a new eigenvector of capital N with an eigenvalue 1 unit up. Okay, so here's what we found pictorially. If I plot on the vertical axis here the eigenvalues of n, then if I find one, little n, then there's another one above it, and another one above it, and another one above it, unless, of course, I run out. But we're going to prove that we can't run out. There's another one above it, and another one above it. Each one being shifted by 1 unit. N plus 1, n plus 2, and so forth. So if I find a solution, an eigenvalue n, there'll be another one at n plus 1, there'll be another one at n plus 2, another one at n plus 3, and furthermore, you go from one to the other by applying the operator a plus. A plus takes you from an eigenvector with eigenvalue n to an eigenvalue n plus 1 and so forth. These, of course, have higher and higher energy because the energy is just omega times n. What about going down? How do you go down? What's the thing that takes you down? A minus. So it's a straightforward thing to prove that, same deal, that a minus on n takes you down. How far down can it take you? Can it take you indefinitely down? Why not? Because the harmonic oscillator Hamiltonian is positive. It's only got positive terms. You cannot get to negative values. The operator is a positive definite operator, which means it only has positive eigenvalues. In fact, it's a theorem that if you multiply an operator by its own conjugate, by its own Hermitian conjugate, its eigenvalues are positive, or at worst 0, or at worst 0. So it can't go indefinitely down. There's got to be a last one. That last one is called the ground state, and it's usually labeled O. You can't go indefinitely down. What does that mean? What takes you down is A minus. So A minus on n takes you to n plus 1, n minus 1, or it takes you to 0. Or it just kills a state, so there's nothing below it. Those are the only two mathematical possibilities. A minus takes you down, or you just run out of states. There are no states below it. That's what happens. A minus on O is just 0. So there's nothing down below n equals 0. The first state corresponds to n equals 0. N equals 0.
Question.
Yeah.
If we take n and then we apply a minus, we get to n minus 1, and then if we apply a plus to that, does that get back to n?
Yeah.
But then a plus a minus times n is n times n.
Let's say it again.
The eigenvalue of a plus a minus is n rather than 1. So if we're applying a minus and then a plus,
Yeah.
is that 1 or n times?
Okay, so let's be careful. Let's. I've been a little bit careless. I've written that a plus on n is equal to n plus 1. But I haven't discussed the normalization of these states. The normalization of these states is not nm equals delta nm. There's a numerical factor. There's a numerical factor. And if we wanted to keep track of that numerical factor, I'm quite tired now and I think we have to quit. But there is a square root of n plus 1 here times n plus 1. Now try your trick again and see what you get. And I think it's also true that a minus on n, I think, gives you square root of n times n minus 1, if I'm not mistaken. I think that's correct. Now what do you want to do? You want to try a plus times a minus on n? Was that the game? Somebody asked me. Okay, let's see what we get. All right, a minus on n gives me, we're going to have a plus, then we're going to have square root of n minus 1. Now, what happens when a plus hits n minus 1 here? It gives me another square root of n. So this gives me 2 factors of square root of n times n. So I was a little bit sloppy. I didn't tell you what the normalization of the states were. The states are not normalized. By that I mean they're not Kronecker delta normalized. They're normalized to some weird factors with square roots of n in them. When we need that, and we will need it, we'll write it down. But it's getting a little too late for all possible details. Okay, yeah. Oh, incidentally, yeah, just one point. Notice that this equation here says that when a minus hits the ground state, it does give 0. Yeah.
Does the ground state have to be 0 or can it be above 0?
Above 0 what?
Well,
No, it has to be 0.
it has to be 0.
Yeah.
Is that clear why it has to be 0?
Well, here, yeah. Yeah, let's see.
Well, square root of 0 is 0?
Yeah.
If the vector n minus 1 is 0, it's a 0 vector. Just as an example.
We can prove it. I'm a little bit tired now, and I don't know what the proof is, but it's a good question. The answer is 0. The answer is that the spectrum of capital N here is all of the integers starting at 0. Okay? So that tells us that the energy spectrum is omega times an integer. There is an h bar in here, and I'll go through the h bars. I'll tell you where the h bars are hiding next time. But it tells you that the energy spectrum is omega times an integer plus the famous 1/2 h bar omega that we threw away. So there's the ground state energy plus on top of it the spectrum of integer space levels. That's the harmonic oscillator. And we'll play with it more, but more important, we'll use it to solve some important problems. Okay.
For more, please visit us at stanford.edu.